Hi, and welcome to this lecture. In this lecture, we will implement a neural network with a single hidden layer for classification. This tutorial will be divided into two parts. The first part is already written out here, and I don't want to spend a lot of time on, just to show you that a logistic regression will not be enough to classify the data. And then the second part, which we will spend a more significant time on, is building our neural model from scratch. I've already defined the function here called the neural network, and we're going to go through each of it in details. First thing we do is we import the packages we need. The Jupyter notebook will be available in the link description. So we start by importing the NumPy, the Matlab Plot, sklearn. Basically, the sklearn will be used for the logistic regression implementation, so we don't have to write a logistic regression from scratch. The Matlab Plot will be used to plot the graphs. NumPy, we needed to create our matrices and everything else really in neural networks. And I just put a random seed in one just to make sure our values are the same all throughout the notebook. So we start by importing these. And in here is the data. So this is just a random data set. As you can see, its values are going to be on the X and Y, with it being either 1 or 0. And then we just reshape that data. So again, this is just a set of data. I just minimized that. Also, it's not so important, but here you will see it visualized. So it takes in the X, the 0 part will be the X-axis, and this will be the Y-axis, and it will be labeled with the label Y here. So you can start this, and here we visualize this data. So we can see that we have dots scattered all over the graph, with red being the label 0 and blue being the label 1. And our goal is to be able to if we were to plot another data here, we would like the algorithm to know whether it's a red or whether it's blue. This is a simple function defining a logistic regression to plot the decision boundary. So let's go through it quickly. So it takes in a model as a parameter. It takes in the X and it takes in the Y. And it plots a graph of the decision boundary using this model. So if we just execute this for now, and here we say we're importing the logistic regression straight from the sklearn library, and we fit our data into this model, and we call the plot decision boundary to build our model with the data on it. And then we calculate the prediction, again just simply using packages straight from sklearn, and we would like to get the accuracy by having this printed. So let's take a look at this. We can ignore the warning, and here is the most important part. We see that the logistic regression has only 52% accuracy, and it fails to classify, well, basically 48% of the data, because it's simply just a straight line. It's not able to curve around and single out the red ones versus the blue ones or the purple ones. So yeah, in this lecture we will aim to show you now how a neural network model actually outperforms the logistic regression when it comes to classifying data of this shape. So here we see mathematically we have the parameters W and B, which is our linear function. And if you remember from the neural network representation lecture, 1 here refers to the can we zoom in? Let's see. Hope this is better for some people. Yeah, that 1 here refers to the first layer, and xi here will be the input data, or it can be also a0 of the ith example. So that will be whether it's example 1, 2, 3, 4, or 5, and this will be the output of the linear function of that example, the first, second, or third example. Then we implement a tanh as our activation function. Can be a sigmoid, can be anything. Again, it takes in the output of the linear function of that example, and now you have a value of the activation function of that first layer. This first layer information is then passed on to the next layer, and as you can see here, xi is now replaced with a1i of the second layer and also the second layer of the real number, and now you have your activation function. You calculate this part here, we apply a sigmoid function instead of a tanh. So we spoke about different activation functions in the previous lecture, and this is how you get your y hat. And if your y hat is bigger than 0.5, then we'll consider that as a 1. If it's otherwise, it would be considered as 0. We then give the prediction by calculating the total, the cost function, basically, using this equation here. So we walked through all of these lectures in the tutorials, and we introduced all of this. So the structure will be divided as follows. We're gonna start by defining a neural network. We're gonna initialize the model parameters. We're gonna implement the forward propagation. We're gonna compute the cost and the backward propagation. So this would look something like this here. We implement the forward propagation. We're gonna compute the loss. We get our loss values along with the new z values, and we're going to implement the backward propagation and update our parameters, the gradient descent. And we have also shown these in the previous lectures. And then we're going to finally put together all of this in a neural network model. So I've already had some spaces here, finishing off with the prediction and tuning the hidden layers. So here we're going to have the first thing that goes in this function is we define the neural network structure, we initialize the parameters, we loop through the gradient descent, and then we're going to calculate our forward propagation cost function, back propagation, and the gradient, and update our gradient descent parameter based on the number of iterations the user would like. So in this case we just put 10,000, but you can define it here. If the user doesn't define it, it's 10,000. You can also delete this, print cost true. The user doesn't define it, but we can also do that. It's okay, and to basically print the cost every 1000th iteration. Here we build a model. We pass in the x, we pass in the y, and the number of hidden layers. We say it's 4, it can be whatever you like, and when we define the neural network structure here, then we're going to have the input and the output with the number of hidden layers. And then this is basically a one hidden layer deep, or one hidden layer shallow neural network. In the next set of lectures, we're going to build a full deep neural network. So let's start by defining our neural network structure. So let's go up and define our neural structure. We start by saying that our sizes will take in x and y. Well, x will be the input data set of the shape, and the y is the labels of the shape. And we want this function to return the size of the input layer and the size of the output layer. So return the input and the output. So that will be a very straightforward code. So let's take in an x and get the shape of 0, and y a little bit here. We can already take a look at the output of this if someone is curious. We saw simply the shape of x. The first one is 2, so that we're gonna have two features, which is x and y in this case, and the output is 1 because it's either gonna be 0 or 1. If it's 0, then it's red. If it's 1, if it's blue, or vice versa. We can also take a look at the full shape. So it's 1 out of 200, and it's the same for the x. It's 2. So x and y, and there are 200 examples of that. So you got the x value stored here and the y value. So that's the feature, the input features, and for the y, you basically have whether it's 0 or 1, and there's 200 examples of that. You can also do this. There you see the array. Okay, so now we have defined the input layer. Now we want to initialize the parameters. If you remember in the lecture, we said we can't initialize them with 0 anymore, but we will initialize them with 1, since initializing them with 0 might just return a linear function. So we're gonna just initialize them with random values. So we have 3 inputs here. It will take in the size of the input layer, the size of the hidden layer, and the size of the output layer. And if we looked earlier down here, we will hardcore the hidden layer for now. In the future lecture, we will show how to build several layers in a deep neural network. We want the return of this to be to be a dictionary, or sorry, is to be a Python dictionary containing the parameters w1, b1, w2, b2. So let's just create a dictionary, but we just return parameters for now. And we can say that these parameters contain the values we need. So we need it to contain w1, which is in our equation up here, w1 and b1 basically. So if we just do this really quick, so w1, b1, w2, and b2. So let's calculate these, which is now more important. We said we're going to initialize them with 0. So w1 is going to be generated by a random value. We have also shown in the previous lecture how to calculate the dimensions. So it will be the hidden layer with the input layer. If you remember, it was NL and then NL minus 1. So the current number of neurons in the current number of neurons in the layer. And this one will be NL minus 1. In our case, it's the input, which is in our case is 2. And we're just going to make it value super small, because if we initialize the values very largely, it might take a long time to learn. So we want to make sure that the values are really, really small. So we're going to do the same for W2. But this time it will be NY, since W2 is the next layer. And NL minus 1, if you remember from our previous lecture, will be NH in this case. So it's very important to get the dimensions correctly. B1 is a column vector, and we can initialize this one by zeros. It will not be a problem. Again, it was NL1 and NY1. So I just try to get our lecture from last time. Here it is. Now it looks super messy, but basically WL was NL, NL minus 1, and BL is NL1, where L was the current layer it is right now, and NL minus 1 is the previous layer. So this is W1 and this is W2. So we're trying to implement this to neural network representation. So now we have initialized our model parameters. Let's implement our forward propagation. So the forward propagation is going to take in two parameters, x, which is the input data, and the parameters. And the parameters here, it being the w1, b1, w2, b2 that we initialized earlier. And by having these two, then we can start our forward propagation. So you need x and the initialized parameters to get z1, and so on and so forth. So this is what you really need to trigger the avalanche of the forward propagation. So we start off by extracting the parameters. So we need w1, and that will be in parameters w1. So from the dictionary that we had earlier here, I can just simply do this and fix the indentation. We need w2 here. We need b1, and we need b2. So the first thing we've done now is we have retrieved our initialized parameters, and now we can start implementing our forward propagation. So it's basically writing these equations here. So let's write it down. So we got np dot w1x plus b1. And then the next step would be a1 np dot tanh z1. Let me start the next one. np dot w2 a1 plus b2, and then a2 in this case is the final output. Let's do this. Okay. So these equations here are the representation of this here. A2 in our case, which is down here, is the sigmoid output of the second function. So if we look here, it's the sigmoid output. It's our y hat value basically being calculated. So now we have initialized our values, and now we have calculated our forward propagation. Let's also create a dictionary. Let's call it cache. It's just a name, nothing special about it. Doesn't do anything more or less. So we want our Z1 to be stored in this cache. We need A1 to be stored in our cache. We need Z2 to be stored in our cache. And we need A2 to be stored in our cache. And then we want it to return A2, which will be then used to compute the cost, and then we need our cache values when we implement the backward propagation. So we already did something wrong. Invalid syntax. Oh yeah, we forgot to do this for the rest. Well, we don't need the last one. Okay, so next we compute our cost. To compute the cost, we will implement the cost function equation here, which takes in A2. So let's just write it up. So we're going to compute our cost. Takes in our A2, which is the output of the sigmoid from the previous function. So the A2 will be the sigmoid output of the second activation of the shape passed, and Y will be the true label vectors, whether it was blue or purple. Red or purple, sorry, or red or blue, depends on how you want to classify it. Looking at this equation, we actually don't need the parameters. All we need is the A2 and the Y in the equation. We need Y first of all to calculate the cost function, which is the M down here. We'll also need the Y to calculate the cost function. So how shall we implement this? We're gonna have here. So I'm just writing out the equation. Like A2, we just passed that, and we're gonna add it to one more bracket, 1 minus Y, 1 minus A2. So if we look at here, you'll see it's this equation in here exactly. And the cost would be the sum of this here, so over M. So if we just take a visual screenshot of this, minus np.sum log props, so we got the minus np.log props, so that's the log props here, and divided by the M is right here. So we get the we now have our computed costs. We're going to return our cost. There will be probably dimensions coming out, so let's make sure we squeeze out any dimensions that we don't need. Yeah, so that's that. So now we have implemented our compute cost. So we started off by defining our network structure based on our input data. We've initialized our parameters, we implemented the forward propagation here, and we computed the cost. Now we're going to do our backward propagation. Our backward propagation will take 4 parameters. So let's start with calling it backward propagation. So this was going to take the parameters. We mistakenly gave the compute cost the parameters, but we don't need that. It's going to take the cache, and if you remember, the cache contains all our linear function values, and it's going to take an X and Y. So yeah, it's just a quick. So the parameters here contain the Python dictionary of our parameters. The cache here contains the input for the linear functions, and X is the input data, and Y is the true labels. We want it to return the grads, and in this case we can say that the grads contains all our derivative value, which is dw1, dw2. So again, we can just think of it as give us back our dw1. Again, we explained this in the lecture. We're just basically implementing the equation equivalent. So B1, sorry, B1, B2, B2. So the goal of this function is to then basically calculate the whole backward propagation. We will need m here in this case, so let's sorry. So I paused the video for a second to check the value of m. So yeah, so I just edited this really quick here, so we know that the number of examples is stored in y.shape1 and not in y.shape0. And then we proceeded with getting our parameters from the cache value from the forward propagation. I realized I didn't click record back. So yeah, now we can we have our m values, we have our forward propagation values. Now we can proceed to calculate our back propagation values. We had these are straight from the lectures, which are basically the values that are here. So the derivative of z at the second layer, the derivative of w at the second layer, the derivative of b in the second layer, and so on and so forth. So we're going to convert this, which we spoke about in the neural network presentation, into code here. So let's start. We write around dz2. So then we need the derivative of that, which is 1 over m. I'm going to fast forward a bit here. So here are our derivatives. We got the dz2, which then we use as an input to calculate our dw2, which is the derivative of the w, or the weights, and then the bias, and then again the derivative of the weights, and then the bias. And that's how we have our backward propagation. We pass these values into the gradient descent, and we have our backward propagation ready. So if you remember earlier, I've shown this here. So now we have implemented our forward propagation, we computed the cost, we implemented backward propagation and update, and now we're gonna update our parameters as we go along. So to update our parameters, we basically need the parameters, the gradient descent, but we need something new here, which is the learning rate. And the learning rate is how fast it should change the derivative, how big it should apply the derivative to learn the values. So we just keep it like that, and the user can define it. So the arguments are the Python dictionary containing your parameters and the gradient you have calculated with your backward propagation. So again, it's pretty straightforward. We need all these values to update our parameters correctly, and then we would need also our gradient descent values. So let's start with that. dw1. So just quickly do this. I'm gonna fast forward through this one also. So now we have our forward propagation values and our backward propagation values, and we're gonna now implement the equation to update the parameters based on the learning rate and the values the user has calculated. Forward through this. So here we have our parameters, the weights and the biases, being updated according to the learning rate and the values you had here, and you can see W1 comes from there. Let's now do our favorite dictionary. Parameters. Fast forward through this. So now we have our parameters and we return it. So now we got our neural network model, which is basically putting all of this together. It will take in X, which is the data set input. It's going to take in Y, which is the labels of the shape, the number of hidden layers the user would like to define, the number of iteration in the gradient descent loop, so how many times do you want to iterate over this to update your values, and print cost if you want the user to print or not. And we're going to return the parameters down here, which is basically the parameters learned by the model that you can use to predict any new data. So let's start by initializing our neural network. So we know we have an X and an Y. and this can be from here for the first thing we have. So we're gonna call in layer sizes and 0 and 1 basically. So we're gonna do this. So we're gonna initialize our layers based on that. Oh, just do this. So 0 is where nx is located, and 1. So take in the value of x and y, pass it to the layer sizes, and take the first position and take the second position, and these are your nx, your input layer, and your output layer. Next, we're going to initialize our parameters. So we already know how to do that. So we're just going to type in parameters. Let's scroll up to our function, and that's the beauty of functions. There we are. To initialize the parameters, we have this, and it returns w1, b1, w2, and b2. So what does it need from us? It needs the input layer, the hidden layer, and the output layer. So we're going to scroll down here, and we just initialize our parameters. And we've done a dictionary. So we simply just parse our dictionary with the values we need. So now I've parsed our dictionaries, and we have the values. And now we're going to loop on our gradient descent with the number of iteration the user wants. So the output we need is the A2 and the cache, and that is from our forward propagation. So where's our forward propagation here? We got our forward propagation, and it gives us A2 and cache. So we just scroll down here, and we do that. Next, we need our cost function, and our cost function gives us back the cost. So it's we can remember that. So we're going to compute the cost. So we can just scroll down back here. So give us back the cost. After that, we need the backward propagation. So we just scroll up again. We have our backward propagation, which returns the gradient descent. So we can just do that right away. So grad equal this. Make sure that, and then we need the gradient descent parameter. So again, we do the same thing. We just highlight this, and we know it returns parameter down here. So we're just going to do parameters equal. And that's it. We have our model ready. So we can walk through this really quickly. So we call in the NN model, the neural network model, and it takes an x and y, which is the input data. With the x and y, it calls in our function the layer sizes. So now we have the input, the shape of the input, and the shape of the output. The user defines how many hidden layers they want. So this is a one hidden layer classification. Don't confuse this with a full-on deep neural network. We then initialize our parameters by passing in the sizes. And the parameters function returns our initialized random variables here. So now we have all these variables, w1, b1, w2 and b2. We then iterate our forward propagation by passing in the x and the parameters. We compute our costs. We get our cost function. We then have our backward propagation, which again takes the parameters, the cache, and the x and y. And then we update our parameters using the parameters, the grades you've collected, and the learning rate. We use the cost so you can see the cost. Basically, it just prints out the cost. On second thoughts, I can see that we haven't used these values, so we can just actually just get rid of it, since the parameters is used directly and we already apply it through here, so we don't have to parse it from our code. So let's look what we have here. We got our parameters, and let's execute this, and we get a name error. Initialize parameters is not defined. I probably haven't copied it correctly. Okay, I'm just gonna restart and run all. Make sure I've executed everything. So we have some errors here and there. So let's see with the backward propagation. Scroll up, backward propagation. What did we do wrong? So it seems like the parameters doesn't have A1, but A1 is right there. A1. So after looking into this, the key error basically means that this value doesn't exist in parameters, and that's actually true. So my mistake was actually right here. Basically, the output of our parameters comes from our initialized cost. So if we look at our parameters here, it returns the real numbers b1 and b2. It doesn't return a1 and a2. Our a1 and a2 is calculated by our forward propagation, and it's not randomly initialized. So I believe if we simply do this, this should now fix the issue. Now we just go execute everything. And now we have another one. Learning rate is not defined. And yes, it's not defined because I haven't passed it here. So the whole model doesn't even take it. Okay, so this was an incorrect thing. With my update parameters has the learning rate. So we can initialize our learning rate, for example, to be 1. I just haven't initialized it. We should have done that. Still complains about it. So since we don't pass the learning rate from here, we can also, we have two ways to solve this issue. Either we remove the learning rate from here and just use the default learning rate, or what we can do is we can make the user define the learning rate. So we can just add another thing here and just let the user define the learning rate. 1. Let's see if this solves it. So there we have the same. Oh, I see. Again, that's the same mistake I've done. We need to make sure it has the cache here since the parameters don't have it. Actually, yeah, this is incorrect. We don't need a1 and a2 when updating the parameters since our equation just needs this. I've seen this, so we just do it that way because we don't need the activation functions here. So let's see what else do we have. All right, so you see where all the errors are. Operands will not be broadcasted. Hi all. So I have now found why does this return an error. So let's restart and run the notebook, and there we get an error. Operands could not be broadcasted together with shapes, and the problem was there were a space here. It's a lot of spaces. So just make sure your dictionary is properly concealed. So if we run it now, also you can see here that I have brought the DW1 on DW2, so this was supposed to be DW2. So now if you just run it, this should also, right, there we go. So we finally see the cost after several iterations, and now we can see that the costs has significantly went down, and it's went down and then it went up again after the 9,000 iteration. So now let's write a function that can show us the prediction on any value. So this function is going to take into two parameters. So let's call it predict, and it's going to, the language is still there. Yep. So we got parameters x, and we will use this. We will pass these parameters to the forward propagation. I realize I've also misspelled it earlier. So taking this and get me the values of a2 and the cache, because you do want the final values able to predict correctly. So with the calculated weights and calculated bias, what is my output? So if it's just give me the prediction when it's bigger than that, then I'll calculate it later and just return the predictions. Okay, and now we can use our earlier function that we had here, plot decision boundary. So we need the model, the x and y, so we just copy this and go back down. And then we're going to use the predict, so we're going to define a function here. So the lambda of x, predict based on the parameters and the transpose of this. Okay, y is not defined because it has to be in capital. And there we go. So this is our last one, our last values. You can see using the weight and bias, it's here in comparison to logistic regression, which we had here. So this is our neural network. What we can also do now is we can plot several hidden layers. So I'm gonna fast forward through this. So let's say we have one hidden layer, two hidden layer. Remove this. Yeah, we have one hidden layer, two hidden layer, three hidden layer, and so on and so forth. Let's move this up here. So this is simply a for loop that will plot several of these. Let's execute it. Maybe we can run from scratch to make sure we have no values flying from somewhere from before. Right, missing one requirement, the print cost. So let's investigate. What did we miss here? So when we defined our parameters in the NN model, we do have the print cost, but it's complaining that we don't have it here. There we go. We got our hidden layer of size. It's executing, so let's give it a minute. And we'll see when it's done, when this star is finished. So here we see how does it look like when it's hidden layer of size 1, hidden layer of size 2, size 3. You can see already when we have 3 hidden layers it starts to improve. 4 even gets better. You see 98% accuracy, but it starts dropping at 5, 20, goes up again, and 50. 100%. Wow. So you can see it has overfit it, or has learned your data very well. So yeah, that was that. Thank you all for watching, and I just want to give credit to Andrew Ng course for this data set and for the functions and for everything else actually. So big credits to him and his team out there. If you have any questions, please post below. Otherwise, I'm gonna have this notebook posted. Thank you.